Okay, in this video we are going to look at satellites, and in particular we will derive a formula between the time a satellite takes to complete one rotation around the parent planet and its orbital radius. So what's a satellite? A satellite is a small body which revolves around a bigger body. So it is like this. You got this bigger body here, and you got a smaller body, and this smaller body is going around this bigger body here, and its mass could be called m. So from that point of view, Moon is Earth's satellite, and in addition, Earth has many artificial satellites as well. Like we launch satellites into orbits for the purpose of communication and remote sensing and surveillance and so many other things. Now this radius from the center of this big body to the center of the smaller body here, that is known as the orbital radius. It's basically the radius of the orbit of this satellite. Okay, so we see that this smaller satellite is revolving around the Earth. Now it is because it's moving in a sort of circular motion. It's moving in a circle, or even if it is of any other shape, this thing is moving around a bigger body, and it's not going in a straight line. So it means there has to be some centripetal force. We know that the circular motion is not possible without centripetal force, without some force acting to pull the object in. So even if thought orbit is elliptical, it is going in circular motion here, so you need someone to pull it in here, you need someone to pull it in here, you need someone to pull it here, you need some force to pull that object in there. So you will need some centripetal force. There will be some centripetal force without which this kind of motion will not be possible. So who is providing the centripetal force here? In our particular case here, who is providing the centripetal force? What agency is providing the centripetal force? If we think a little bit, we should be intuitively able to come up with the answer that centripetal force is being provided by the force of gravity. It's an important statement. Provided by the gravitational force. Someone has to be there. Some agency has to provide this force. So let's first look at this object here. Let's first look at the centripetal force required for circular motion of this satellite. So centripetal force required is equals to m v square or r, where v is the speed of this small satellite in its circular path, and r is the orbital radius, because this is moving in a radius of r. And where it's coming from? It is coming from the gravitational force. So your gravitational force is equal to Fc here. So gravitational force is providing the centripetal force. So they will be equal. So what we have here is gravitational force is G capital M small m divided by r square, and this is my centripetal force. They're equal. Now I can simplify this equation to find the value of v. So I want v all by itself on one side, which means that I need to get rid of this r from here and get rid of this m from here. To get rid of this m, I put a m in the denominator, but I do that on both sides. To get rid of this r, I put a r in the numerator, but I do that on both the sides. So what I have is, on the right hand side, I'm I make it the left side now. So on the right hand side, I am left with v square, and on the left hand side, which becomes the right hand side now, is equals to m gets cancelled with m. This r cancels get with the square here, so gm over r, and that tells us that v is equal to the square root of gm over r. What is this giving us? It's an important equation. It's an important lesson. It is giving you orbital speed of a satellite. So what we have gives us a speed of a satellite, and we can see that it does not depend on the mass of the satellite. Satellite could be big or could be small, but if it is in an orbit of radius r around a planet of mass m, then it will have this velocity. It has to have that much velocity. Okay, and as I told you, it's a important relationship. It's a established relationship, which means that you can use it as it is without deriving. It's an equation that you can use in your calculation straight away. Now what we're trying to find here, we is trying to find the relation between time period t. What is time period t? Is the time the satellite takes to complete one rotation around the planet. And what other thing, and the other quantity that we are trying to find relation is r. So we are trying to find relation between t and r, where r is the orbital speed. And we can start with this equation, but we can start with the equation for t. We know that t is equals to, we are trying to find, what we're trying to find, trying to find one rotation, means we are trying to find one circumference divided by the speed. So time taken to complete one revolution is one circle. Let me put in a layman's language, one circle divided by speed. Yeah, so in a circle, when the satellite goes around in one circle, it's traveling that much, it has to travel that much distance, and its velocity is v. All right, so that we can reorganize it, and we can say v is equals to 2 pi r over t. Now in place of v here, we can write this equation now. So I'll write that in place of v, I'm writing a square root of gm over r is equals to 2 pi r over t. Squaring both the sides, when I square both the sides, I get gm over r is equals to 4 pi square r square over t square. And I will reorganize it so that I have t square all by itself on one side. To do that, I need to get rid of t square from here, so I will do t square here and t square here. Then I get t square gm over r is equals to 4 pi square r square, and there's nothing there, should have written properly. Let me write again, 4 pi square r square. Now I need to get rid of this g, everything else from the left hand side. So to get rid of gm, I will divide by gm, but I'll do that on both the sides. to get rid of this r from here, I will time with r, but I'll do that on both the sides, and that gives me t square is equals to, they cancel out here, I'm left with only t square on the left hand side. T square is equals to 4 pi square, let me write again, I'll write like this, 4 pi square over gm times r cube. Now this is a very important relationship, and we can write it in words as well, that the time period depends on the radius of the orbit. In particular, we say that t square is proportional to r cube. Now this is an observation which was made by Kepler many years back. Kepler practically studied the time periods and radius of these different planets around the sun, and he proposed this relationship, and that relationship was verified as well. And this is the relationship we have here. What we have here is that if you have the mass of the planet and you have orbital radius, you can find out how long it's going to take to complete one revolution or one rotation around the planet.